Hello everyone, this is Sayim from the University of Southern California. I was a postdoc at Weill Cornell Medicine during the submission of this abstract. In this talk, I will be glad to summarize the recent findings of our research work called MRSaiFE towards the real-time prediction of SAR in 3 Tesla and 7 Tesla. We extend the feasibility to 10 body models. Here are the financial support that we received during this work and the disclaimer due to FDA regulations. Ultra-high field MRI promises improved signal-to-noise ratio, which provides better spatial and temporal resolution as well as new pathways for neuroimaging. However, UHF comes with the lowered imaging wavelength and higher specific absorption rate compared to lower field strengths. As seen in table, imaging wavelengths are comparable to human anatomies. This causes higher EM variation as well as SAR variation for human anatomy, and also SAR variations from subject to subject, making it difficult to set input power for RF coils. Although SAR is one of the major limiting factors, there is no real-time local SAR monitoring capability for today's MRI scanners. Current state of the art is to use numerical simulations, which requires the subject-specific tissue segmentation and cost durations on the order of days. Recently, we start to see CNN-based predictions for accelerated tissue segmentation and also subject-specific SAR estimations. In this work, we extended the MRSaiFE to 10 body models and analyzed the effect of different hyperparameters on the algorithm performances. Eventually, we fed our network with a grayscale MRI-like image and estimated their SAR distributions by using 2D unit structures. In order to mimic real-life practices, we moved body models into different landmark locations. At 3 Tesla, we used the body coil for torso imaging. At 7 Tesla, since there is no bore-mounted body coil available yet, we used a single-channel head coil for brain imaging. All the coils were driven in CP mode from 2 ports with a 90-degree phase shift. Total dataset was composed of almost 120,000 images. We split it into training, validation, and testing sets for approximately 80%, 10%, and 10%. Algorithms were trained and tested for each body model separately so that we generated a library of models trained for different body mass indexes and field strengths. Different unit structures with 2, 4, and 6 expansion and contraction layers were utilized. The hyperparameters investigated in this study were given in bold. We implemented these models by using TensorFlow with Keras backend and ran them on the hardware given here. The overall performance results for different network complexity, learning rates, and optimizers are given here. We observed that the learning rate of between 10 to the power -3 and -5 works similar for all architectures. Also, the cumulative time required to test a single slice is increasing exponentially for higher number of convolutional filters. We have found that a 4-stage network with 64 or 128 filters at the initial stage is a good compromise among them. Here we can see the body model specific performances for the optimal network complexity. 3 Tesla results are depicted in the top row for 5 body models, and 7 Tesla results are depicted in the bottom row for 5 body models. We can see that the MSE of algorithms are below 1% for all optimizers and body models. Similarly, the structural similarity index metric for ADAM optimizer is above 85% for 3 Tesla and above 90% for 7 Tesla head imaging. In addition to quantitative results, qualitative results show very good agreement between the ground truths and prediction results. At 3 Tesla body imaging, we can see that the predicted maps clearly shows the intensity distribution of the SAR maps with very low MSE and very good SSIM. Similarly, at 7 Tesla head imaging, SAR distributions are estimated with very low MSE and higher SSIM due to higher resolution. We also masked the ground truth and predicted hotspots using the top 15% of local SAR values. We obtained a mean SSIM of 97% and MSE of 1.5% when SAR maps were normalized to the mean of the ground truth. In conclusion, we have shown that the 2D CNNs can be used to predict local SAR distribution with very good quantitative scores. Optimal complexity for local SAR estimation problem requires 4 contraction layers only. This complexity allows for real-time predictions, usually within a few milliseconds with a personal laptop. We have seen that more than 90% average SSIM and less than 1% MSE for 7 Tesla head imaging is possible. Similarly, more than 85% average SSIM for 3 Tesla body imaging is also possible. When we consider the other studies in literature, we can say that the subject-specific SAR estimation for in vivo clinical settings may become feasible soon. And thank you for your attention.